So here we're required to again plot the magnitude of the transfer function, um, and also to find the break frequencies based on the plot. So first step is we convert the transfer function to its standard form. So we get this one. So on the standard function, we have a constant factor. We have a 0 at the origin, a simple 0 or a simple pole, and two similar simple poles that we can actually combine in the plot. Okay, so these are the plots of the factors. So this is our constant. Here is our 0 at the origin. This is our so this one is this one. So again, to plot that, you have to find uh, omega equals 4. So here it is. Before that frequency, h dB is 0, and after that makes a slope, positive slope or negative slope of 20 dB per decade. So this one has a slope of negative 20 dB per decade. Okay, um, we can combine this, and this is the plot. So we look for 10 radians per second. Before that, it is a 0, and after that, it makes a slope, which is equals to negative 40 dB per decade. Okay, we combine the individual plots, and that should give us this one. So how was that plot obtained? So at omega equals 0.01, we add this and this one. This one is a 0, so we get this one. And then from there, the plot should follow the slope of this. Okay, and up to here, where the slope and the slope cancel with each other, so the plot should be constant. And then from here, the slope should make a turn and follow the slope here. Okay, so this one is 20 dB per decade, and this one is negative 40 dB per decade. So the break frequencies are this point and this point. So that's 4 and 10 radians per second. Let's have another example. So here we have a transfer function, and we are to plot the magnitude of the transfer function, the straight line Bode plot. So we need to convert this expression to its standard form to show the basic factors. So we factor the denominator first, and that should give us these roots. So they are real roots. but factoring the numerator will give us a complex root. So that means that the numerator must be a quadratic zero. So we need to convert this numerator into an expression that so it looks something like this. Okay, so we need to convert this similar to this one. So this one. Okay, so we can do that by making this a 1. So we need to isolate the 4 there. So we will get this one. Combining this, and this will give us this constant gain. Manipulating this 7 over 4 to make it like this, that will give us this one. Okay, so this is the final, or this is the standard form of the expression, of this expression, where we've substituted s as equal to j omega. So we have a constant gain, a quadratic zero, and 3 simple poles. So here is the final form of the transfer function in standard form. Now we're ready to plot the straight line Bode plot. So first, um, let us plot the quadratic zero. So this is the quadratic zero. So to plot the quadratic zero, we need to identify omega k and q sub 1. So take note that the standard form of the quadratic zero looks like this. So to get omega k, we compare it here. So this must be omega k. Okay, so that is the value of omega k. And to get this, we are going to compare it here. So that must be equals to 4. And since we already have omega k, we can get q sub 1. Take note that this is greater than 1. Now we're ready to do the plot. So we plot it in our semi-log scale, where the horizontal scale is in terms of omega k. So we identify first omega k. So let's say it is located here. So first we need to identify the asymptotes for omega much lesser than omega k and omega much greater than omega k. So we know from our documentation that for omega much less than omega k, HDB is approximately 0 and the phase angle is 0. And for greater than uh, or omega much greater than omega k, HDB there is given by this, and the phase angle is 180 degrees. So let's do the plot. So for omega much less than omega k, so this is the asymptote. So HDB is 0. For omega much greater than omega k, it looks this like this one. So it is a line with a positive 40 dB per decade slope, and it passes at omega equals omega k with a value of 0. Okay, um, It is 0 because at omega equals omega k, we have 40 log omega k over omega k, so that makes a log 1, which is a 0. So 0 times 40, that will give us 0. So we have a 0 there. For omega equals 10 omega k, uh, uh, 10 omega k, that will give us 10 omega k over omega k. So that will be log 10, which is a 1 times 40. That will give us 40. So that's why we have a 40 here. For omega equals 100 omega k, you, that will go through the same process as this one. So you will get this point here. So that that's why we have a 40 dB per decade slope. Now, we also need to identify the exact location of HDB for omega equals omega k. And from our documentation, that is given by this one. Since Q1 is greater than 1, so log Q1 will be a positive. So we have 14.47 for Q1. We take the log of that and times negative 20. That will give us this value for the magnitude. And for the phase angle, that will give us 90 degrees. So plotting our quadratic zero will give us this plot. So here's the plot of our quadratic zero again. So let's plot the remaining factors. So for a constant gain 0.8, that will be the plot. For our simple pole, this one. So this is the plot. For this simple pole again, this is the plot. It's plot here. And for the last simple pole, this will be the plot. Okay. So combining all the plots, we'll get this final plot. So to explain the plot, so it starts at 0.8. So this follows the constant gain plot. And then until here, it starts to go down because of this and this one, and up to the lowest point here. Okay, so where this is the combination of the lowest point of the quadratic zero, somewhere here, so in minus 14.47 plus the simple pole here. Okay, so it goes up to this point, and then from there, since the quadratic zero plot starts to go up, so the plot goes up until here. It flattens out because the slope of this and the slope of this combines to offset the slope here of 40 dB per decade. So it becomes a flat line until here where it starts to go down again with a slope that is the same as this one.